So gone through just vector operations here in this section. So now let's take a look at how these vectors, uh, how we represent solutions using vectors, which I think some of us in class have already kind of gotten um, in the habit of doing, and I think I usually present the solutions in vectors here. But here, let's get more in depth and more specific in representing uh, solutions of a linear system as vectors, right? So let's take a look. Let's say we have an augmented matrix that is in reduced row echelon form, right? So let's say here it looks something like this. All right, and I'm told that it is augmented, right? So as we can see, it's non-homogeneous. Right? And we have here two pivot columns corresponding to the variables x1, x2, right? And we got our set F is the columns 3, 4, and 5, but 5 is uh, our vector of constants here. So we're going to have two free variables, right? X3, which I'll denote as T, and X4, which I'll denote as S. As you may notice, the textbook just leaves them as X1, X3, X4. Again, fine if you want to do that. I think it's just a matter of, for myself, preference to just use the parameters S and T. But feel free to leave them as X3 and X4 as well, right? Uh, so now going back here to our system. So now let's write the solutions for the other variables, right? So looking at row 2 there, I can write x2 plus x3, but that's t, minus 3 x4, but that's s, equal to 0. So solving for x2, we get x2 is 3s minus t. All right. And now looking at row 1, we get x1 plus, right, 3t, right, 3x3, which is t, minus 2x4, but that's s, equals to 4. Okay, and then again, solving for x1, we get 4 plus 2s minus 3t. All right. Okay, so now we can find, or we can write our solution vector, right? Taking all that we have up here, x1 was 4 plus 2s minus 3t, and then here 3s minus t, and then t and s. All right, and again here, st are just some real numbers. All right, and before we just wrote our vector in this form here. Now here we're going to go a step further here using, again, row operations. All right, our vector operations, I should say, excuse me, not row operations. The vector operations that we define in this section, and I can write this here as the sum of three vectors. Right, the first one, if you notice here what all these entries have in common, or excuse me, not in common, what makes up these entries? Either a constant or some parameter s or t. So I want to break it down into its components here, right? So its vector form would be, here the first part is going to be the constant. Now, looking at those four entries, entry 1 for x1 has a constant, 4. It's not attached to any parameter. It's simply the constant 4, right? Now, all the other entries in a vector do not have a constant, so those would be treated as 0. All right, that's just my constant vector c. All right, now the other one corresponds to a parameter, right? The parameter, let's say s, right? So here looking at this one, my next vector would be all the entries that correspond to the parameter s, right? So here that would mean 2 for the first gen, 3, entry 3 for the second entry, and then 0 for the third entry, and then, excuse me, 2s, 3s, and then s for the fourth entry. Right? Now, one thing to notice here that s is the parameter for x4, right? So notice that the other free variable, right, is x3, so that will not be dependent on x4. Hence, we can see there's a 0 there, right? And vice versa, as we'll see here. The third component here is what has a parameter of t, so negative 3t, negative t, t, and again, the other free variable does not have a parameter of t, so it has a 0 in that case there. And I can go even a step further and rewrite it. Remember, s and t are just real numbers. So I can write this as s2301 plus t, negative 3, negative 1, 1, 0. All right, and this is the vector form of a solution, right? Where we have some vector here made of constants and then others with some parameters. Again, will depend on the number of free variables that we have as to how many of these parameter column vectors we have. Okay, now our textbook has a theorem here, so I'll bring this up here. So theorem VFSLS, the vector form of solutions to linear systems. So this states that suppose that A augmented with a column of constant vector B is the augmented matrix for a consistent linear system. Okay, so strictly talking about consistent systems of m equations in n variables. Right? Let B be a row equivalent m by n plus 1 matrix in reduced row echelon form. Suppose that B has r pivot columns, and these are the indices, while the n minus r non-pivot columns have indices in F. And then we define the vector C and U sub j in the following manner. Now, you may want to look at this and it looks really complicated, right? But here's what you want to get from it, right? The C vector is the constant vector, so it's going to be 0 for sure if it's an element of, if I, the subscript, is part of the free variables, right? Because those will be described using parameters. All right. And then here, and then excuse me, the other part would just be the part of k n plus 1. So really it's just what is at the end of the constant, of the augmented part of it, right? And that's only for the columns that show up, the columns that are dependent, essentially, right? Now looking at our example here, right? Oh, before I go into that, let's just kind of go through the rest of the excuse me, the rest of the notation here. For the other vectors, these u, so it'll be 1, right, here when it's an element of f, right, the free variables, right? So each free variable will have a column entry that is 1, 0 when it's not, when it corresponds to the other free variable, and then the opposite of the b that we get in the column of the constant vector. So all that means here of the, excuse me, that are in the dependent variable rows, right? So all that means here, looking at our example here, okay, so here this is our vector C, and then here this is our alpha 1 U1, alpha 2 U2, right? So it's saying that for any consistent system, right, I can always write it in this form, right? Where that 1, notice here, corresponds to our free variable, right? That 1 there. Now these other values, right? So for the C, going back to our original one, that corresponds with what's out here, right? 0, 0 in this case. Okay. All right, and you see the 1, 3, 3, negative 2. Hence, you see the negative part over there. Right? Negative 3, positive 2, etc. Right? Because you're moving them to the other side of the equation. All right, so that's all the notation means. Again, what you want to get from that is that if the system is consistent, right, then the vector form of the solution, which I have here, will always be able to be written as what's called a linear combination here of column vectors, right? We'll have a constant vector, and we'll talk more about that in a second when we are talking about homogeneous systems. But for now, this is just all that theorem I showed up just a while ago just corresponded to consistent systems. So the system may or may not be homogeneous, right? It applies to either one. Okay, so it can be written in this manner as a linear combination, right? And then here, from here, you can say, you can essentially come up with instances of the solution, right? So what if I let S be 1 and T be negative 1, right? So now you can write it as a linear combination of these three vectors. Okay? All right.